here in the lecture hall. Every day there's a new surprise with this technique. And Marco is the HDMI input of this Wacom tablet, and I don't to switch it back. But now I know it, so I learn every lecture. I learn something new. Sorry for the delay, as I said. So now switch this chat on. So if there are problems with Kasano or so, if you have questions, just write in the chat. And you, if you see something in the chat, please inform me. It's difficult in the lecture to see it. What have we done in the last lecture? So we discussed transmission of stochastic signals over filters, let's say. Just content here. So it was here. This is the last lecture here. So we said we have an TI system, so a linear time invariant system described by the impulse response, because it's discrete time what we're talking about. And in the frequency domain, this would be transfer function obtained by discrete time Fourier transform, of course, in this case. And then we said we have a sequence here at the in, concrete realization, a sequence at the out. First, we derived, always assumed Weitz and stationary processes. Yeah? First, we derived correlation between, and but we used this more or less to obtain the autocorrelation at the output. We said autocorrelation function of this filter is just the autocorrelation. It's just the autocorrelation function at the in. And we need to do the convolution with the impulse correlation function of the impulse response, which is deterministic. So the input signal is stochastic, the output signal is stochastic, and this is the impulse correlation function of the filter impulse response. And you should know this just from the seminars. Yeah. Discuss deterministic energy signals, yeah, or periodic signals, which are also deterministic. Yeah. And you should know that you can write this G correlation function as a convolutional product, simply. So it's defined as a time domain integral. And then even more important probably is that if you take a look at the power spectral density at the output, the power spectral density at the output is just the power spectral density of multiplied with magnitude squared of the transfer function. So this is like a power transfer function, because the transfer function g of s says how is the amplitude spectral density at the output related to the amplitude spectral density at the input. This is g of f. If you squared the magnitude, this is just how is the power spectral density output related to the power spectral density. This is not surprising. So, and then we said, okay, we just introduced here this power spectral density. Yeah. Said, okay, for this example, AMI autocorrelation function. I've done the discrete time Fourier transform and obtained power spectral density. Yeah. Then we discussed the characteristics. And today we switch to time stochastic processes. And as long as these processes are real valued, there's no difference in the characteristics. So the autocorrelation function is an even function. Yeah. This is very helpful because if you calculate the value at a given time shift, you know the time shift with m, and don't need to calculate this at -1 if you know 1, for instance. Yeah, this value, it's always an even function. Of course, the autocorrelation function for real processes is real, yeah, power spectral density, because if this is a real function, the Fourier transform is always also even function. Yeah. The difference is, of course, always if you have discrete time signals, yeah, then the Fourier transform is periodic. So it's not surprising that this is a periodic function. Yeah? And of course, if you just insert numbers, yeah, to obtain a frequency description, here you can't see any time, the time index m, see any frequency. Yeah? So if you do the discrete time Fourier transform, oftenly, not always, oftenly, yeah, you just use here, if you take a look at textbooks, which is fine, but we don't do it here, that you just say, okay, just show you the definition, yeah, it should be discrete time Fourier transform. Here is the definition, yeah, that you insert the time domain signal, let's say, yeah, and then you have a unitless frequency because you don't see any time in the concrete time in discrete time signal, yeah. But here we assume that these samples here, yeah, correspond to a time, let's say t naught. This t naught, the reciprocal value, is the sampling frequency. Yeah? But of course, you could say, for instance, t naught is, let's say, 1 second, and this sampling frequency is 1 hertz. Yeah, because this is not contained here in this description. Yeah, so oftenly you don't see this t naught here, don't see here fs. If you do this, yeah, if you say, for instance, fs is 1, then this is just 1. Yeah, but important to note is that this corresponds always to the Nyquist frequency, so half of the sampling frequency. This point. If you know the spectrum from here to here, so from 0 to the Nyquist frequency, you know everything. Because you know this is an even function. So if you have this characteristic, you know this characteristic, and the rest is periodic. So in MATLAB, for instance, yeah, if you have a discrete time signal and you obtain the Fourier transform, usually you plot it only from 0 to by 2, so to the Nyquist frequency. So this is, because there's all the information here, we have shown that the spectrum is periodic. So, and then we said the total power is basically contained, yeah, because it's periodic, and you have to take care, yeah. The total power is not the integral over the power spectral density from -infinity to +infinity, because this would correspond to an infinite value. So this would be, by the way, possible, yeah, if we would replace this autocorrelation function, this discrete time autocorrelation function, if we to replace this by a sampled autocorrelation function where we use direct delta pulses here. But anyway, the total power is basically in this interval from -fs/2 to fs/2, or if you want, from here to here, it's the same, over one period. And because we have this, let's say this t naught here in the frequency domain description, yeah, you see if you integrate this is the average power, one half in this example. If you just integrate this cosine, or let's say, is it sine squared characteristic, 1/2 minus 1/2 cosine is a sine squared. If you integrate this from here to here, you see this is unitless, and you would end up with fs/2, right? If you integrate this from here to here. So you have to normalize to find the average power integral from here to here with fs. This is shown. So phi xx of the transform is obtained, yeah, by this integral. And if you just want to see the average power, depending on your power spectral density, you integrate from fs/2 to fs/2. Nyquist frequency to Nyquist frequency. But here you have to use this 1/fs. So even if we denote this as power spectral density, we have a discrete time description, yeah? Take care with physical interpretation, like in physics. But today we switch to continuous time, and then everything is fine with the units, yeah? So, and then we said we learned already, yeah, that if we power spectral density or the autocorrelation function at the in, know the system description, so impulse response, transfer function, we know also the power spectral density at the out. Ended up with this example, so if, let's say, we have this, you remember, how could we obtain this alternate Mach inversion? We said we could do a differential encoding of the bits and then take the difference, yeah, of two neighboring bits. So this, we started with this example. Yeah? There was this last lecture. There was this description. These are the differentially encoded bits. And this can be realized by a filter. So I take the actual differentially, subtract the previous differentially encoded bit to obtain a new symbol, xn. So this is a filter. This can be realized by a filter. And said impulse correlation function of this filter would look like this. This is the filter impulse response. Yeah. If I multiply Gn with Gn plus m, sum up, I end up with this for different m. So an even function. Yeah. So, and this autocorrelation function, yeah, differentially encoded with this, I obtain correlation function of AMI. But here we talk about power spectral density. So I could say this corresponds in the frequency domain by this G of f magnitude squared. Yeah? It looks like this. And if I multiply this with the power spectral density at the input, this is the input of this filter. So this is the power spectral density of this differentially encoded. So if you only take a look at the continuous part, it's a constant. Bits are statistically independent. It's just a constant. But if I multiply this by the transfer function, I get again this sine squared characteristic, which is basically described by this filtering. So, and the discrete components of the spectrum disappear completely because they correspond just with the zero crossings here of this transfer function. You see, if you multiply this with this, you get exactly power spectral density, which we obtained in this example from the correlation function. But here we said, f the power spectral density, multiply it with g of f squared, and we obtain spectral density at the output. So now we want to discuss a small, why can we interpret this really, if we take a look at the power spectral density, as the spectral distribution of the power. Why is it possible? With our knowledge, we can prove this. I show you, this is not a proof in the classical sense, it's example you will see. And then we switch to continuous time, and there is just one node. There is also subsection which is denoted as, let's say, a parallelogram estimation. This would be a method. This method, you can obtain an estimation of the power spectral density by means of MATLAB, whatever. It's a computer. So you have, let's say, data. Yeah? Want to estimate the power spectral density. But I decided to do this not for discrete time processes. I do it, this derivation for continuous time, and then I show you the slides, how you could implement this by means of a discrete time Fourier transform. This is really important because often you have measured data, or you say, okay, it's too complicated to calculate the autocorrelation function. From the autocorrelation function, the spectral density, I want to numerically, or I want to check my results if these make sense. So numerical methods are really important. Yeah, but I do this in the next lecture. And before we do this, continue, I say basically, does the power spectral density for these discrete time processes really show or describe the spectral distribution of the power over the frequencies? How can we prove this? Yeah? And then we shortly switch to so-called cyclostationary processes. Then we go to continuous time. So now a new lecture. So let's start. So let's say we start with this, just with a question. Does x of f, say we did process as xn. So we started with autocorrelation, and we are still assuming White's stationary processes. Yeah. Then we used discrete time transform to obtain this domain description, which we notice as power spectral density. Yeah. But this is just a definition. The operators, yeah. Does phi x of f describe? Spectral distribution power. So therefore we get this as power spectral density. So and let's say we just take a look at this example, but it could be, of course, any example. Yeah? Just show here again where at least this power spectral density looks similar to the power spectral density of A. So let's say here this is the frequency. Yeah. Let's say 3, 6. This is the sampling frequency. Yeah. This would be the frequency. Here is fs by 2 and so on. This is minus fs. Let's say sine squared characteristic here. So here it was 0, the spectrum. There was the maximum value. 0. Like an offset for sine. It's like so. So on. Say this is exactly the old example. Then we said, if we just want to see the total power, and to obtain the total power, we have to consider this area. As I said, yeah, this is the total area. So this corresponds to the total power. But again, this is not just this area. To divide this area by fs. Yeah. If the advantage, if you would use unitless frequencies, yeah, you don't this normalization. This would be the total power. Maybe I write this again. So m is 2. You know, for stationary processes, yeah, the autocorrelation function does not depend. So correlation function for a time shift of 0 is a constant. So it does not depend on x. And this would be just 1 by fs, integral from fs by 2. I write it again. S by 2 x of f. For continuous time, you just can write integral from minus infinity to plus infinity. So the total area under the power spectral density is the total power. Yeah. So now ask the question: is, say, phi x of f1 times delta f times 2 Now what is F1? This is a certain frequency, and we want to find basically power which is contained the frequency F1, and not only exactly at this frequency, but at the frequency range, which is narrowband, yeah, centered at F1. Let's say we have a small frequency range. Width of this frequency range, let's say this is delta F. So, and then we take a look at this area. Now, take care always, if you read a book or if you read a paper or so, and there is a power spectral density mentioned, you have to ask, is this two-sided, as in our case, or one-sided, as in physics, quite often they present results. Since it's two-sided, yeah, we have to consider the same, of course, at the left-hand side. So it's impossible just, if you want to measure a power at a frequency F1, certain bandwidth, you have to do because we use this two-sided description, yeah, we have to do the same at minus F1. So this is this symmetry, yeah, because here we also have this delta F. So, and then if now Fxx times at F1, yeah, so this is the power spectral density at this frequency F1 times the spectral width times 2, and now again look here, divided by 1 by Fs, yeah, this is just a normalization which we require since we have discrete time. Really, on the relative signal power at F equal to F1 within a small bandwidth delta. So delta F is very small. Small. I use this abbreviation for bandwidth, delta F. So how can we prove this? To check this is quite easy, because we can say we have shown that that y of F, so the power spectral density at the output of F is just the power spectral density at the times squared. Now we assume a bandpass filter is a very passband of this delta F. Assume band bandpass filter. Band filter. As in the figure, yeah. So I show it in the figure. We are only interested in, it's clear, yeah. So we draw a figure. Let's say I draw it in red. This, oh yeah. F. Say here we have exactly this frequency F1, exactly this frequency minus F1. This is G squared. Assume band, such an ideal bandpass filter with a brick wall or rectangular shaped characteristic passband. Here, F1. Yeah, so the frequencies within this bandwidth delta F pass. This is the passband. All the other frequencies, in a technical sense, are suppressed completely. This is a bandpass filter. Now, it's like this. because we have the same at the left-hand side. And then we know if we have this filter, we would filter our input signal here, where we want to know how can we interpret this distribution, is this really power distribution? So we know if this is the input signal or this is the power spectral density of the input signal, and we multiply this with this. What do we obtain of the output of this measuring equipment, let's say, measure something. So, and what do we obtain at the output? Like this. So let's say I just show, so Fs would be, this would be Fs2, is F, this is minus Fs by 2, and this would be y. Then the original characteristic looked like this, right? So this is this dashed curve. This is the characteristic at the input. So, but now if I multiply the blue one with our bandpass filter, what comes out is this. So every here is 0, 0, 0. Then we get exactly this band, this characteristic. If the bandwidth is small enough, don't have to take care that this is not absolutely constant. Look here, the power spectral density near 1 frequency passband range is not totally constant. Assume it's more or less constant if this delta F is quite small, of course. So, and then we have the same, let's say here. It's minus F1. It's minus F1. It's like this. It should be absolutely symmetric, of course, And then we know. What do we know now? We can now calculate power at the output of this filter. Because this is what we know. This just comes from the inverse discrete time Fourier transform. Now we know my2. This is just, of course, 1 by Fs, so this normalization, but this is the important story. Fs by 2, S by 2. If you look, this is, of course, nearly, in our case, nearly, because we have a infinitely small delta F, but this is nearly phi xx of S1, because only F at x1, F1, we have the passband, times delta F. If we neglect just power spectral density is not constant in this range, times 2, because two-sided spectral density, Of course, you could describe everything if you draw a figure, You could say one-sided, two-sided. By the way, there is MATLAB function how you could estimate, and with this function you can basically, based on this periodogram estimation, which I describe in the next lecture, this is implemented. Then you can say two-sided, one-sided, there's an option. So now it's two-sided, therefore there we have this 2, and this just comes due to our normalization. So this Fs, this is not astonishing. You see, really the power, in this frequency range is really described by the spectral density at this frequency. I know this is absolutely simple, what I've shown here, but it shows this is not just a mathematical description, this power spectral density. It shows, in reality, the relative power frequency range. And of course, practice, many cases, we have so-called ergodic processes where we can switch from ensemble averaging, so averaging over different organizations, to time domain averaging. So if you want to measure this, now I go back, you see it again. So if you want to, this was the lecture from yesterday. from last week. Yeah, if you want to measure this, yeah, you say, okay, here I have a quite long realization of my process, but only a single realization. Single realization. I do only one source, yeah, let's say, which generates this coded data, AMI coded data. I don't need a huge number of these signal generators operating at the same temperature, under the same conditions. That's one. Then I have here a bandpass filter. Yeah? And of course, if I want to find the power spectral density of this signal, yeah, I use this bandwidth filter, I could use, yeah, and I change the center frequency, and then I measure the average power in this small frequency range. Of course, if I decrease the width delta f, we discussed before, yeah, get a more precise description, but we need to wait longer in order to find a good C3 measure of this mean power. Yeah? But you don't need to build this equipment, let's say 10, you just have one realization, yeah, and you measure, you do the averaging over the time. For instance, this EMI coded process, this is an ergodic process, wide sense stationary ergodic process. Why? It's simple to understand. Let's say, this AMI coding could be done by putting bits, okay, differentially encoded bits, yeah, the input of, but these differentially encoded bits, model is that we assume they are statistically independent and identically distributed, of course. Yeah? They always have a probability of 1/2 and so on. Then, if you switch from one bit to another bit or excerpt of this signal, there is the surprise in the new bit is the same as if you use a different data source, because they are statistically independent. So if you have statistically independent symbols, the process is always ergodic. And if you do a filtering, it's still ergodic. So you could switch from ensemble averaging, which is always assumed if you write expected value, time domain averaging. In practice, to obtain something, to measure something. Now, a last thing, we'll find this topic especially important to find a good way, let's say, to discuss the power spectral density of modulated signals. But I introduced this here because it's, say, very easier to understand, not very easy. And this is a cyclostationary processes. So I just have to take a look which cyclostationary processes. 1 second. This would be 2, 3. So this is 3. Okay, to take care, yeah, I write here again, wide sense. Sense. Cyclo. Stationary processes. This is a weaker form of wide sense stationary processes, and these processes have a function, but periodic for the time, so it depends on the time. Autocorrelation function depends on the time. Time is now a time index for discrete time processes, yeah? But is periodic. We start with a very simple example. Argue at the end, as you will see. Yeah. Say, okay, according to our model, the process is, let's say, this cyclostationary. But we can derive from this model another model where the process is stationary, as you will see, at least Weizsäcker stationary. Interested in higher order descriptions. Yeah. To understand this, I present a simple example. Then you will see, okay, I believe that this is just this cyclostationary T of a source really depends on our assumptions, on our models. Yeah. Example. Assume we have a sense stationary process. And so to say it's a process, I write here n from minus infinity to plus infinity, and we just write according to the xn's, yeah, just from 0 and neighboring xn are identically distributed. So I just write it here, identically distributed, independent, identically distributed. This is what we assume. And we assume, this example, let's say that Px, I don't need an index here because they all have the same distribution. Say Px of 0 is 1/2 of, this is also 1/2. So ones and the zeros have the same probability. So now I just draw an excerpt of this Weizsäcker stationary and also Weizsäcker ergodic, completely ergodic process. Yeah. It could look like this. And you will see later why I draw this. Okay. So I say I have a certain index. This is the time index n. Just draw here one randomization. Start at, here is 0, n equal to 0. Let's say is 1, 2, 3, minus 1, 2, and so on. It's just an excerpt, of course. Yeah. I draw it, let's say the values I draw in. Then let's say this value could be, for instance, 1. This value could be 0. Yeah. Time index is an integer. Discrete time processes are indexed by integer values. Let's say this is again 1 and this is 0. Let's say here is also 1, 0, and this is 1. As I said, this is an excerpt. Yeah? If I would build now a short time average, yeah, it does not need to be 1/2. So it's an excerpt. Just show it like this. Okay? So this is 1. Yeah? So the values are 0 or 1. This is one realization. So and now to obtain the autocorrelation function for this, thus you know this is simple to obtain. Correlation function for this Weizsäcker stationary. Oh, sorry. Switch to blue. Looks like this. Say this and this, this. So the correlation function. What does it look like? This is, you should know it now. So we take a look at the time shift m. Draw here phi xx of. The simplest of course to start with the value at m equal to 0, and this is the mean power always. Yeah, what is the mean power? 1 squared is 1, 0 squared is 0, which is just 1/2. So you see this value here say it's 1/2. I wrote in blue. So, and then how can we obtain the other values? Neighboring samples here are statistically independent. Therefore, all the other values are just the square of the mean value. Square of the mean value is 1/2. Even if we would obtain this over an infinitely long time interval, could obtain it also by ensemble average. So we know this, we just assume we know the statistics. So the mean is 1/2, so the mean power is 1/4. So this value is just 1/4. The other m's. This is just how our autocorrelation function looks like. By the way, just to show this, yeah, if you want to obtain the frequency domain description of this, it's always beneficial to say, here we have 1/4 plus 1/4. Then this is like a sequence, yeah, of such 1/2 values, yeah, which goes from -infinity to +infinity, which gives in the frequency domain also a sequence of direct pulses. Just so the continuous part of this spectrum is 1/4 value. Okay, now let's assume we build a new process now, and this is cyclostationary process. Yeah. Now we switch to this new topic, let's say. This is quite thick. What is 101, yeah? Sure. What do you mean with 101? It's random. It's random. This is just an excerpt. Yeah. You cannot say I used these 7 values also to obtain the autocorrelation function. The correlation function is based on statistics. To do the expected value, you know how this is defined. This is for large excerpts, not m. M is the shift. So this is expected value of xn times xn plus m. Expectation means you average over huge number of realizations. Yeah. So, and to find these expected values, yeah, use the probability mass function, or for m equal to 0, because then you see xn squared. This is basically all the values of x multiplied with the probabilities. Say you obtain the probabilities, yeah, because you consider in reality, yeah, each number of realizations, yeah, then you measure the number of ones and the number of zeros. So, but I said you can obtain the same, let's say, empirical probabilities if you consider a huge time domain excerpt, which goes from -infinity to +infinity, let's say. Then you can also obtain the same statistics. That is, 0 has a probability of 1/2. 1 has a probability of also 1/2. It's the same information about this. This is what I say. But you can never use just this short excerpt to say, okay, probability is this and this. You see immediately, yeah, if you would use this, here I have 1, 2, 3, 4, 5 ones, but only 3 zeros. This is not enough. Large numbers for information coding. So, and now assume, is this a new column? Assume new process to quite simple. Let's say we define the new process, yeah, And the values, yeah, so the samples are given like this. They are exactly xn, so I write here capital X to say it's a random variable. So, and it's the same, the random variable yn is the same as the random xn, say for n, or let's say it's xn by 2, then it's even simpler. And it's just 0 else. So it's quite simple to understand. So if we insert, let's say, 0, get this value. Insert n, or concrete realization, n equal to 2, we get this value, and so on. Then we just append zeros. This is what you would denote in, let's say, digital signal processing if you have a concrete signal. Say this is upsampling, you just insert 0. For whatever reason. And now if we draw an excerpt just to understand this, what happens? Looks like this. So here's the original value. It's a 1. It's n. 2 now. This is 2, this is 1, this is 4, this is 6. This is now 8, so on. This is -2, 3, -4, sorry. These are the original values. Six. This is this value. But now we have new values. I try to use a similar color. Should be the same color. Okay, I do it with the same color, but let's say a little bit thick. Yeah. These are the new values. Append each original value with a 0. Quite simple. So this is a new realization, yn. It's like this. Now let's say if all the realizations are defined like this, all the realizations, then we take a look, for instance, at this, let's say, expected value of. Now I take a look at the concrete time n. To do this is always operator for ensemble averaging. So we have a number of realizations. So you say this is one realization, but I draw figures of thousands of other realizations from different sources, which look different, at least at the numbers of this n. Because now if I start at 0, let's say just I want to take a look, yeah, at the average power at the time 0. So you know, we describe just if this is a realization, you describe xn squared as instantaneous system theoretic. For time discrete signals, it's a little bit to understand, but for continuous time, it's easy to understand. Yeah. So the square is the instantaneous power. Now we just take a look at the average power averaged over a different realization at the time 0. So, and I would say this is expected value of, of y 0 times y0. So this is, of course, y0 squared. Yeah? But here we say we start with m equal to 0. So, and this is, of course, expected value 0 squared. What do we obtain? What would you say? If I just take a look here at the time 0, yeah, but I assume there are thousands of realizations, and all the realizations come from different sources, so they are statistically independent. So what is this value? So this is 1, of course. It's what? It's like in the previous one, it's 1/2, of course. Yeah. Half of the cases, I have the value. This is described by this probability. This is I have a 0. But now I take a look at expected value by 1 to the square. That's it. So now I take a look here, where I always insert the 0. And what is the value? 0. So now at 0, we see the expected value depends on the time. And of course, we could say this is the same for is equal to expected value by 3 to expected value by 5 to the square, and so on. So we see even the mean power on the time index. But we also see that the expected value of y2 is equal to the expected value by 4, and so on to the square. So at odd numbers, yeah, of this time index, we get this power 0 always, because we have done this upsampling where we inserted the 0. It's this constant power of 1/2. So you see, at least if you take a look at this mean power, we have a period of 2. Even now, if we would investigate the autocorrelation function for different time shifts, get a periodic structure. So the autocorrelation function becomes periodic over the time. I don't talk about periodic over time shift. This is important. So we write now expected value of yn times yn plus m. This is our autocorrelation function. And also expected value of yn. So the first moment depends, and because there are two such things, on time index n. But both values periodic is a period 2. So, and the question has, is there an idea how could we map this process to, let's say, a stationary process, White-Sands stationary process? What could we do with the realizations? To say, if we then do ensemble averaging, yeah, of the realizations, then the process is stationary. Is there an idea? In our model, we assume the realizations. So you say, I build, let's say, signal generators, yeah, and this upsampling, just insert 0 bit, yeah. Do this with an experiment. All the students here at the university build their generators and they generate the sequences. But in this model, according to this model, where we say the process, yeah, depends on the original process described by this equation, yeah, we assume that all the realizations are synchronized. And as soon as we say we don't have this synchronization, this is stationary. Because if we would assume that all the realizations could have an additional delay between 0 and 1, and the 0 and 1s are likely, so we introduce a time shift, which is random for all the realizations. This is just another model, and this is not to say, oh, how could you do this? Because this could be closer to reality than this model. Because who says, why are all these signal generators synchronized in time? Then I need atomic watches to synchronize them. It's not unrealistic. So if this process is stationary or not, somehow depends on our model. So we could say, okay, good process is right sense stationary by introducing a time delay, I mean, you could insert any time delay, but it's enough between 0 and 1 to the process, to the realizations. N. So let's say I build a new process, let's say Zn. Values of Zn are Xn. Let's say theta or so. This theta is equally distributed 0 and 1. It's a theta. It's just a time shift. This technique is a name. It's denoted as phase randomizing. Why phase and not time thing? Now, if you have a sinusoidal wave also and you introduce a time shift, this corresponds to a phase. Probably the name for is phase randomizing. But literature, this is denoted as phase randomizing. What we obtain is also, if we then take a look, the autocorrelation function of Z, autocorrelation function of Z looks like the time averaged autocorrelation function of this cyclostationary process. Basically, if you want to obtain the same result, if you would introduce this random delay, get the same result as if you do a time averaging over this time-dependent autocorrelation function. Now let's look here. Let's say we only look at the second moment. The second moment is either 1/2 or 0. This original cyclostationary process. So this means the mean value is just 1/2 plus 0 divided by 2 is 1/4. This is not astonishing that the new second moment is 1/4. Even if you take a look, time domain average, you would say statistically, data bits, the original data bits, in half of the cases are 1 and half of the cases are 0. But I insert a 0 after each bit. So now the new second moment is 1/4. So say what is the new, basically the other values of the autocorrelation function. Of course, for even time shifts, and they are not 1/4, they are 1/8. So, and then we could say basically that the autocorrelation function, but I show you then another example of Zn of M is equal to the time averaged autocorrelation function. Let's write this like this, expected value of Xn times Xn plus M. So this autocorrelation function depends on the time, but we just insert a time. This is the operator. You don't need to do the time averaging from minus infinity to plus infinity, it's enough to do this over one period. Period is 2 in this example. So I could say this means time averaging. Here we only need to do this over 2 samples. Yeah. 2 samples of the autocorrelation function. Sorry, y, of course. This was a mistake, sorry. Said the original stationary process was x, and the cyclostationary process was y. Yeah. So of course I need to write here y. This was my mistake. Yeah. I talked about the cyclostationary process, of course. Yeah. This was really a mistake here. Yeah. So in information theory encoding, I inserted here 2 to say I do averaging over 2. So this is enough. But just say over 2 samples. Yeah. In this example, that is one period. So the autocorrelation function, the new autocorrelation function, yeah, is periodic. If we time averaging over one period, exactly as if we would introduce this random delay sessions, yeah, which is, in my opinion, often closer to reality than the original. The way I just mentioned this, I don't write it down. You could expand this technique. Say in the extreme case, I could also say, let's say I have a periodic signal, just a periodic signal. Assume a sinusoidal wave. Know, hopefully, from the seminars, the determination function of a deterministic signal is just periodic. For instance, the autocorrelation function of a sine is a cosine, always with the same frequency. Cosine shaped the autocorrelation function. Define this as a time integral. So it basically describes this autocorrelation function for deterministic signals, as in this case, a linear dependency between neighboring the mean, see, yeah, between 2 neighboring signal values, this autocorrelation. Now you could say, if I use this deterministic periodic signals, yeah, if I would produce an ensemble realizations and all synchronized, then this process, of course, is it's not random, yeah. It's of course not a Whiteson stationary process. So I just draw a figure, but then I delete just to say, yeah, let's say we have a sine wave here. Next realization, it's the same sine wave. All the realizations like this sine wave. But now, if I introduce random time shifts for the sine waves, which are uniformly distributed according to the period of this sine wave, all the realizations have different delays. And then I could map this deterministic and for sure not stationary process into a Whiteson stationary process. But get exactly the same ensemble average as if I would do the time averaging as described in the seminar. It's just story behind. Yeah. Now I show you an example which you can find on the slides. So TC slides. So I have to go to the web. Oh, what's this? Chat, there is a question. So what have you can't figure out. Sorry. Thank you. Process after process. Oh. Many times process, which the T, yes. Now, we could build a new process which is Whitesand stationary. So, sorry, now you could read it. I switch to the C. Just say we could use, I mean, we have a non-random process, a non-random signal. Okay, it's a periodic sinusoidal signal. But we could say we could map this into a random stationary process if we introduce a random to the realizations. So basically the random thing is just this random delay. And then I just say sample averaging is exactly the same value correlation function as time domain averaging. This is quite similar to what we are doing. So now we go to the curves here, coming engineering. Take a look at slides. Here, it's an example, which is so-called Manchester coding. Understand what happens. Exactly here. It's Manchester coding. See cyclostationary process, at least Whitesand cyclostationary. So say we want to transmit a bit stream. Yeah, these are the original bits. Okay. Here the time index is k. Yeah, because for the coded bits, yeah, I use a different time index basically, which is n. So these are the coded bits, and this encoding, this Manchester encoding, is quite simple. If I want to transmit a 1, a binary 1, I transmit 1, 0. If I transmit a 0, originally, I encode this as 0, 1. So each 1 is mapped into 1, 0. Each 0 is mapped into 0, 1. So this is not channel coding. This is denoted as line code, because we want to change our spectral density of our signal in discrete time signal. We want to remove DC components, at least the continuous part of the spectrum, at f equal to 0. Why we need to do this in some cases? So if you introduce, if you have a real source, yeah, and you want to transmit data, it could happen that a lot of adjacent data bits are just 1, or a lot of adjacent data bits are just 0, and you can transmit this over a high-pass filter, channel with high-pass characteristic. What you need to ensure is a so-called DC balance. So this means, let's say, a short time average, some numbers of bits, or let's say 20 bits or 100 bits or so, yeah, needs to be more or less constant. Yeah. Weight of each code word, independently in your original data, is just always 1/2. It's 1 plus 0 plus 1 divided by 2. What you see here is basically these are the original bits. Here, these are the original bits in this B. This number here, 1, 2, 3, 4, 5, this means this is the realization. Because I've shown here 4 realizations. But in order to do averaging over the realizations, yeah, to draw much more realizations, of course, an infinite number. So now here this is the, now let's say we want to calculate the value over the realizations. So the expected value of the power, the instantaneous power or the expected value over this. So, and then we say, statistically, if you do this Manchester coding, we only take a look at x, not at get in half of the cases, of course, because the original bit is in half of the cases 0 and half is 1. We get 1 to the square plus 0 to the square divided by 2. Even if we look here at n, this is n equal to 0, this is n equal to 1. Even if we look here, get in half of the cases here a 1, because originally the bits were in half of the cases 0. So here the average power does not depend on the time, but still the process is not quite stationary, because now let's take a look at the time shift of 1. Start at n equal to 0. So we compare this and this. So x0 times x1, the expected value. And what is it? See, what is the expected value of x0 times x1? 0. It's always 0. Because this is within one code word. I look within one code word, but there's always 1 0 and 1. So, and this means if I take a look here, x2 with x3, it's also 0. I compare x6 with x7, it's always 0, expected value. But if I compare x1 with x2, so this is still the time shift 1, of course, there is a value, because now I take a look at two different code words. So this is the second bit of the first code word, and this is the first bit of the next code word. Statistically, in one of 4 cases, first code word will end up with a 1, and the next code word will start with a 1. So in 1 by 4 of all cases, I get 1 times 1. And therefore, if we take a look at the autocorrelation function, of course, at m equal to 0, it does not depend on the time, n. The value is just 1/2 function. But if the time index is an even number, the correlation function for m equal to 1 is always 0. But if I switch to an odd number for the time index, the autocorrelation function is 1 by 4, because in 1 by 4 of all cases, one code word ends with a 1 and the next starts with a 1. And then for larger time shifts, I always look in 2 different code words. The statistic of 2 1s is, of course, 1 by 4. And now, in order to see that, now let's say the question, is this scheme for transmission? Say, ooh, how could I obtain this? Now I manage this autocorrelation function. Depends on the time. How can I obtain a power spectral density? Okay, say, I just do it over time domain averaging, but you say, is this allowed? Because this process is not stationary in but this just depends again on our model. If we switch now, let's say, to random shifts, this is shown here, and I've shown here basically 1, 2, 3 realizations here, concrete realizations. Okay, here is another realization, concrete realization, where this random time shift is just 0. This is just here in these lines of this table. So, and then I draw here the code words, and I inserted that you see where is the end point of a code word. I inserted these dots here, okay? So all these are start here, the code words, and end here. They start here and end here, and so on. And then I inserted the time shift of 1 for other realizations. So statistically, half of the realizations have the original time shift, have a time shift of 0, sorry. And the others have a time shift of 1. You see now the start of a code word is here to here, here to here. And now, what would happen if we now do the ensemble averaging? If we only take a look at the realizations which have this delay of 0, I get the original problem, yeah, I calculate the automation function, let's say at n equal to 0, with a shift of 1. Then I take a look, I get this value of 0. But in the other half of the realizations, if I take a look at n equal to 1, to 0, and n equal to 1, yeah, so n is 0, but m is 1. Originally, since I shifted this, now I take a look at, let's say, 1 and 2. This is the same, yeah, as if I consider the autocorrelation function for half of the realizations, let's say for n equal to 0 and m equal to 1. This is where I talk about, because this depends on the time. And in the other half, I take a look at 1, n equal to 1, or n equal to 3, and so on. Then if I average, take the average value, yeah, this is the same as if I average over the original autocorrelation function here for this process, which depends on the time. So I just need to do averaging over 2 samples again to obtain the autocorrelation function of this case. So I just want to tell you, if it's simpler to obtain this autocorrelation function, yeah, I would say I can map this in a time-independent function, which corresponds to a random phase, just by averaging over the time. Then the value of the autocorrelation function here is 1/8, of course, at m equal to 0. So this was just a short, by the way, I think, as I said, yeah, in the next lecture, we do this periodogram estimation. I just show you here a figure. This is how it looks like, this power spectral density of this Manchester coding. What you see in blue is basically an estimation of this power spectral density, where the red line, yeah, does not contain the DC component of the Manchester code, because there is a DC, of course. You only transmit zeros and ones, and therefore you have a direct delta pulse, yeah, at f to 0, because there is a DC signal. This is what you see here in the simulation, but for this figure, I only draw the continuous part of the spectrum. You see, really, if you do this Manchester coding, see the continuous part of the DC components. Yeah? Quite similar to this AMI. Transmit the ones as -1 and +1. Then you also have basically sure, yeah, that your mean value of the signal for this AMI is basically 0. Because if you transmit a 1, the next one is transmitted as a -1. So you ensure a balance of 0. Here you ensure a balance of 1/2. But this is quite often used, for instance, especially in fiber optics. So now we switch to continuous time. There's not so much to say about continuous time. The difference is, yeah, discrete time processes, yeah, are random variable, sequences of random variables indexed by an integer number. This is the time index, n, say. Yeah. Index is a real value. This is the time t. Don't write x with a subscript t, we write x of t. But this is the meaning. So now we switch from integer valued index to real index, and this is the time. Basically, the same definitions. We have the first moment. This expectation can be calculated. Say I consider all possible amplitudes at this time t. Because I calculate this, I consider all amplitudes and weight these amplitudes by the probability density at this time t. This is the probability density function at the time t, as at the time index n. And don't do one mistake, please. Often we talked about discrete time processes. We used here the probability mass function instead of the probability density function, because we said we also have discrete amplitudes. This is often the case. We talk about data sources, and they are 0, 1 and 0, yes, or let's say 0, 1, 2, 3, or whatever, yeah. But you could also have continuous valued amplitude. Then you know that you need to switch from the probability mass function to the probability density function, because you have continuous amplitudes. Yeah. For continuous time signals, usually you have to use the probability density function. Assume that you have an analog signal. So it has all the possible amplitudes. So but this means this is the probability density function at the time. Then this is the second moment, of course, yeah, which may depend on the time. Remember, I had an example of a non-stationary process where the second moment increases with the time, and this was this random walk. So if I took a look at the different values n, variance or the second moment increased with this n back, yeah? And then we define the autocorrelation function. Generally, it may depend on the time. Mostly interested in Weizsäck's stationary processes where the first moment and the autocorrelation function are time independent. So this is just a fixed value, and this is just a value which only depends on the time difference, tau. Now we denote this as tau, the time difference. What we denoted until now as m is now tau, time difference. This is the expected value of x of t times x of t plus tau, corresponding to discrete time xn times xn plus m. This is the equation, and I think, let's say, if I would start with this expression, lecture, stochastic signals, processes, and I said, this is the definition of the autocorrelation function, you would say, I don't understand this. But this means, again, this is the probability density function. Yeah? Take a look basically at the statistics over a huge number of realizations. And this is the statistic of x at the time t. This describes the relative probability. It's a probability density function. Then we compare this to the probability density function at the time t plus tau. This is joint probability density function. Sometimes you see that they insert here xt and yt, but this is not important because this is just a given value of this joint probability density function. So this is the whole story basically. And again, we are interested in Weizsäck stationary processes, yeah, and then everything is independent of time t. Then we have exactly the same properties as before, as long as we are assuming real valued processes. This is what we are doing still doing. Assume real valued processes, because then we get really nice and simple characteristics. This is tau equal to 0. To 0, see the average power, which is time independent, averaged over the sessions. This value is the largest value. The autocorrelation function for other taus cannot be larger than this value. Say it's an even function. This is shown here. And we still know, if we take a look at large time shifts, we can assume that the random variable xt and the random variable xt plus tau, the random variables, are statistically independent. Therefore, for large tau, if there is a limit, this limit is just value to the square, as before. It's exactly the same. So, and then we also discussed what happens if we have systems and if we have Whitson stationary processes. So we assume we have a Whitson stationary process. Let's say a realization here at the input, and we take a look at the realization at the output. You see the process after filtering is still Whitson stationary. It does not depend on the, as you see in our derivations, the result does not depend on the time index. See, the new autocorrelation function is the old autocorrelation function, and the convolution is the impulse correlation function of this impulse response of the filter. Even more important in the frequency domain, power spectral density at the output is the power spectral density at the input times G of f squared. Everything the same. And here's an example, and I tended to do the description of so-called additive white Gaussian noise today, but now we have to shift this to the next lecture, no problem. So we start with a very important example. This is continuous time process, random process, which describes an interference, and this is additive white Gaussian noise. This almost any transmission scheme suffers from this additive white Gaussian noise if the transmission distance is large. So if the signal is attenuated between transmitter and receiver, then you will see receiver noise at least. So and this noise is, for instance, thermal noise, because all the electrons in a wire, in each wire, they move if the temperature is larger than 0 degrees. This is just a definition of 0 degree Kelvin. It's movement of the electrons. They move, and therefore, if you have a resistor, for instance, and you have a quite sensitive equipment, you can measure a voltage, and this is a noise voltage. This noise voltage just interferes with our signals. In any case, so of course you could cool down your receiver and then you have less thermal noise, but you have still other noise sources like noise from transistors. Optical communication, you have from optical amplifiers which are used for larger distances. This noise is caused by spontaneous emission photons. So I just say any transmission, almost any transmission suffers from noise, and usually, because there are a lot of dual components which contribute to this noise, a lot of electrons, huge number, can model this process as Gaussian distributed, and oftenly, not always, but oftenly, power spectral distribution, this noise power over the frequencies, is almost constant. At least this is a model. It cannot be constant for all frequencies. It's just a model. And this model says in the bandwidth we are interested in, signals used for transmission, we can oftenly assume that within this bandwidth, this power is constant. Discuss this in the next lecture as an example to this pedogram estimation. Thank you. I'm sorry for the